Hello everyone, I hope you are all well. My name is Bendjahene. I am a PhD student at Eurosteel University, Algeria. I would like to present a paper on the subject of ported connections, and the title is a simplified analytic model for T-stub component with preloaded ports. The purpose of this work is to propose the analytical model, which takes into account the bolt preloading effect on the axial behavior of tensile zone of the end plate bolt beam to column connection. This work includes the general introduction of the end plate bolt joint with the passage on T-stub behavior. Then we present analytical model valid in the case of preloaded bolts. This proposed model will be validated based on the experimental results from Percy and Jasper. Afterwards, the parametric study is also undertaken in this study in order to identify the influence of geometric and mechanical parameters on behavior of T-stub. Finally, this presentation will be ended with conclusion. End plate bolted joints are largely used in steel frames because it's cheaper to manufacture, economical in design, and quick to implement. The end plate bolted joint is the most widely used in the practice. According to Oracle tree, the tensile zone of the end plate bolt connections is utilized by two T-shaped elements assembled using two-port row, figure 2. In general, the T-stub behavior in tensile zone depends on the flange rigidity and the possibility of its plastic, the potential irrigation. Three possibility plastic cross mechanism can arise, depending on whether the flange is thin, relatively thick, or rigid. When the thickness of flange is thin, figure 3a, tip 1 occurs and the formation of four plastic hinges come up. Two hinges are located at the board lines and the other two hinges are located at the flange to web connection. When the flange is relatively thick, figure 2b, the formation of the two plastic hinges at the flange to web connection and the failure of the board typify type 2 mechanism. Finally, if the flange is rigid, figure 2c, the third cross mechanism will involve only bolt failure. In this article, we focus only on the simple one, namely type 1, which is governed by plastic deformation in flange. Now, we are going to present an analytical model in the case of clouded bolts. In this model, the T-stub with the four bolts in the tensile zone is modeled as the simplified supported beam, composed for the central span 2, 3, 4 and two lateral spans 1, 2 and 4, 5. The T-stub is subjected to a concentrated vertical load, F variable in intensity, and applied to the middle of the central span. T-stub flange is supported at two contact points 1 and 5, simulated by two simple supports, and the reaction at each point is equal to the prying force. The prying force is located at distance and prime between the board and the tip of the flange. The flange is also subjected to two other reactions in the points 2 and points 4, each produced by the force B, which is axial force in each bolt. The 2 points where the bolt force acting at the bolt axis P are represented by two elastic supports and separated by distance m prime between the web axis and the bolt. The bolt length is taken equal to the sum of the thickness of the flange and that of the washer. The flange T-stub is assumed to be assimilated as a rectangular section of active with B effective and the thickness Tf. Many assumptions are considered in this model as string hardening starts from plastic regime, the board plate interaction is taken into account, constitutive law of the material is conventional, the line of plastic developed in a critical area, and we use different geometry parameters. The incremental calculation method is adopted here, and the analysis is undertaken in elastic, plastic, and ultimate regimes. The proposed analytical model follows the sequence of formation of plastic hinges up to the limit states. Under the effect of increasing load, the T-stub is supported to undergo double curvature during bending. An elastic calculation of T-stub leads to the moment diagram shown in figure 6. Each step corresponds to an increment of applied load. In the first place, the preloaded force became zero when the bending moment in the middle, M3, at the flange to web connection is equal to M2, its moment at the bolt. The second maximum elastic moment is reached at the middle span, when the applied force reaches the value Fe. In other words, M3 to equal M elastic. This moment is determined by relation 1. The prime force, the board force, and the vertical displacement are given respectively by relationship 2, 3, and 4 in the case of presence of preloading force in the bolts. Plastic calculation is always carried out following the first step of elastic calculation. In this operating phase, the loading is applied in an incremental and decreasing manner. First, the plastic moment Fp is reached at the flange to web connection, when the applied force reaches the value of Fp. Secondly, the flange to web continues to undergo additional bending deformation over the anterior section until the sum of the moments in the point 2 equal the MP. The plastic moment of T-stub flange is determined by the relationship 7. The shape of deformation and diagram of bending one in a plastic regime are shown in figure 7 and 8. In elastic regime, the prime force, the port force, and the vertical displacement are given respectively by the relationship 8, 9, 10. Phase 3 is effective for F superior than Fp. The flange T-stub continues to deform until ultimate condition. This step concerns the phase of strain hardening before cracking of the flange material. In this regime, there are two ultimate phases. Firstly, the bending moment at the section flange to web connection becomes mu equal m3. Secondly, a new bending moment at the bolt line reaches the value mu. Mu represents the ultimate moment of T-stub flange determined by relation 12. The shape of deformation and diagram of the bending moment in the ultimate regime are presented in figure 9 and 10. The prime force, the port force, and the vertical displacement are given separately by relationship 13, 14, and 15. Validation of analytical model concerns only the test 1 prototype tested by Bertie and Jasper to undergo the collapse mechanism 1, and it's the case of T-stub with preloaded bolts whose value is 60.7 kN. The comparisons are made in terms of force displacement curves. In figure 11, we present the geometric configuration of prototype used for validation. We use different geometric properties to those considered in Rocco 3. Figure 12 shows the dimension used by our model. The geometric and the mechanical characteristics of the flange and the bolt for the prototype test are also reported respectively in the following table 1. Figure 13 illustrates nonlinear behavior anti-collapse of the prototype type 1 obtained from equation developed for the proposed analytical model. The good superposition clearly shown that analytical model allows a good prediction of T-stub behavior and for considered failure mode. The parametric study is also undertaken in this study in order to identify the influence of geometric and mechanical parameters on the behavior of T-stub. The various parameters are the distance between the web axis and the bolt and prime, and the mechanical characteristic of the flange T-stub. Series of 3 specimens is produced. The specimen test 2, test 3 are similar to the prototype test 1. The only difference lies in distance and prime. As for the specimen test 4, the geometric characteristics are identical to those of prototype test 1, but mechanical characteristics are different. In specimen test 4, the ultimate limit of flange cracking is taken equal to 794 MPa, according to true law behavior of flange for prototype type 1. The table 3 summarizes the detail of the geometric characteristics of different specimens used in the parametric study. Comparison of the force displacement curves of different specimens and the prototype test 1 is illustrated in figure 14. The comparison of the force displacement curves from the analytic models shows that the reduction of distance and prime generates the increase in stiffness and the resistance capacity of the specimen, but on the other hand, the reduction in the capacity of deformation. As for the last specimen, test 4, it was found that the ultimate limit flange influences directly the formation capacity of T-stub, taking into account conventional law of the material avoids completely brittle collapse of T-stub. The values of prying force and the port force are presented in Table 4, Table 5, and Table 6 for specimen Test 2, Test 3, and Test 4, respectively. It's clear that the effect of the force preloaded has remarkable effects on the elastic domain. In the same line, this impact also influences the plastic and the ultimate domain. Immediately, the disguise in distance and prime makes the port preloaded effect more important in elastic region. According to the satisfactory result from the analytic model, it turns out that the analytic model remains the appropriate approach for daily tasks of the engineer and the design office because it's simple in its design and quick and practical in the hand calculation. On the other side, taking such geometric and mechanical characteristics analytically can falsify the prediction of the force displacement curve. Thank you for attention.